Hi, everyone. This is Michael. I'm going to be doing today's lecture. I'm going to go ahead and wait until probably 3:05 to actually get started for anyone who's still trying to log on to this call. Thanks. All right, it's a little before 3:05, but I'll go ahead and kind of start with my preface. So the exciting thing is, since 2 days ago, our enrollment in this summer school has grown from 150 to almost 200, which is very exciting. And we span a huge range of backgrounds, starting with freshmen in college through fifth year PhD students, through professors and industry professionals. And uh, this also not only encompasses age, but also very many disciplines. So we have a lot of nuclear engineers, but also a lot of non-nuclear engineers. And we're trying to make this a summer school that is accessible and useful for everyone. So this is a kind of fundamentals lecture, going back to the basics of neutron interactions and introducing um, introducing cross sections as a concept. So if you're familiar with neutron interactions and cross sections, this lecture is probably not for you. And we'll get to kind of the more niche things, more advanced things, starting later this week and early next week. So if you get bored and need to leave, feel free. We won't be offended. Similar to last time, we will have a couple people moderating the chat. And during Professor Pozzi's lecture, we were happy to see that even some participants were getting involved in the answers. So I'll pause every now and then for questions. Feel free to throw them in the chat and either someone will answer or Will Steinberger, who is currently hosting this meeting, will jump in and pause me. The other thing is I'm going to be writing notes today just because I prefer to write instead of do lecture slides. But because my tablet's on the table, I'm going to keep the camera off otherwise the view is up my nostrils, which is probably good for everyone if I keep the camera off. So with that, I'm just going to go ahead and jump in. So we're going to start with neutron interactions. And neutrons are my life right now. I detect them and depend on them to tell me about systems. And we do that by observing their interactions with other matter. And in particular, neutrons interact with nuclei at a close range. So kind of the analog to this is gamma rays interact with electrons, and that's going to be the main point of tomorrow's talk. And we have some main types of interaction. So I'll list them here and then we're going to go through them. So our main types of interactions are scattering. And within scattering, we have two flavors or types. So there's elastic scattering and inelastic scattering. And then we have absorption. And within absorption, there's radiative capture, capture that leads to transmutation, and fission. Now, for physicists in the room, physicists typically call absorption capture and capture absorption. Nuclear engineers typically kind of use the opposite definitions. And it's actually pretty hard sometimes to tell which one people are talking about. You'll have to use context clues. But for this course, this course being today and the rest of the summer, we're going to be assuming that capture is a subset of absorption. So we'll start with elastic scattering. So in elastic scattering, elastic means that kinetic energy is conserved. And scattering means that the particles that are interacting stay the same. So when we say that kinetic energy is conserved, it's still allowed to be transferred. So the kinetic energy may be transferred. As long as the total amount stays the same. And oftentimes it will be transferred due to conservation of momentum and conservation of energy. So a picture of what this looks like is you have a neutron. Oops, that's So Sean Clark really likes neutrons being blue, and I've been conditioned as such. So a neutron will come in, interact with a nucleus. So that's the before, and the after picture is the particles have changed direction and kinetic energy via velocity. So more of a, this is a kind of the simplest reaction out of all the different types of interactions. So now we'll go to inelastic scattering. Oops. So in inelastic, we still have that it's scattering. So the particles are still staying the same. But now the inelastic means that kinetic energy is not conserved. So if the kinetic energy is not conserved, so because the energy initial must equal energy final due to conservation of energy, the potential energy plus kinetic energy initial equals potential energy final plus kinetic energy final. So if the kinetic energy is changing between initial and final, it means that the potential energy is changing as well. And so for people who are familiar with Q values, it means that this interaction, in a sense, has a Q value. So what happens is when the potential energy changes, the target nucleus gets excited. And oftentimes, the excited nucleus will de-excite by emitting a gamma ray. So the picture that I'll draw here is we have a neutron. Will come in and hit uranium-238. And then, so that's the before, and the after is we still have the neutron, and we still have the uranium-238 because the particles stay the same, but the uranium-238 might emit a gamma ray. So kind of the chemical equation for this is initially we have a neutron and a uranium-238. What this goes to is a neutron plus uranium-238 still. And I put a star here because this means that it's in an excited state. And then the last step is, again, still neutron plus uranium-238 plus the gamma ray, which comes from the de-excitation. And what this means is the energy, so the initial neutron carries energy. And by exciting the uranium-238 and then having that 238 kick off a gamma, which has some energy, the final neutron has less energy than it began with. So this is scattering. We'll move on to capture next. well, I'll say is I'd say the parent header here is absorption. And then within absorption, there's capture. And then within capture, there's transmutation and radiative capture. So we'll start with transmutation. So in transmutation, the neutron is absorbed by the nucleus. And this means that the nucleus is now in an excited state. And the nucleus is going to de-excite by emitting a particle. So this particle could be, for example, an alpha particle or a proton. So an example of this interaction, we could have a neutron interact with, let's say, boron 10. And then what happens is, the very end result is that we're going to have two particles coming out. One is going to be helium-4. The other one is going to be lithium-7. And we can write the chemical formula for this as neutron plus boron 10 becomes helium-4 plus a lithium. Because we're looking at the nuclear level and not looking at electrons, this helium particle is actually an alpha particle, or they're the same. So unlike scattering, our products are completely different from our reactants. So a less violent version of capture is radiative capture. And I'm going to be facetious about this to kind of show that the effects are similar. So the neutron is going to be absorbed by the nucleus. Which means that the nucleus is in an excited state. And so particles don't like to be in excited states. They want to be in the lowest energy state, lowest excitation state as possible. So the nucleus is going to de-excite. And this time it's going to de-excite by emitting a gamma ray. So we'll draw a picture for this. We have a neutron. And this time we'll say uranium-235. And the after picture is, since the uranium eats the neutron, it's going to become uranium-236. And we have a gamma ray coming off. an equation form. It's going to be a neutron plus uranium-235 becomes an excited uranium-236, which becomes a uranium-236 plus a gamma ray. So I'll introduce a quick aside, more of a nomenclature sidebar about binary nuclear reactions. So binary nuclear reactions are when you have two things going in and two things coming out, roughly. So suppose I have the following nuclear reaction. Some A plus X leading to a Y plus B. I can abbreviate this as X and then A, B in parentheses, Y. And in this case, AB is the type of reaction. So from the example above, we could write this as uranium-235 plus a neutron, the particle coming out. So A and B tend to be the projectile, and then X and Y tend to be the larger nuclei. Then we have uranium-236. And so we would call this an N-gamma reaction. So in a different example, if someone said alpha N reaction, this would mean that an alpha particle went in and neutron particle out. So we'll continue to use this nomenclature throughout the course. So we have one more interaction to discuss. This is not a comprehensive list of all neutron interactions. There's still things like spallation out there. But these are the ones that we're going to focus on for now. So the last one, still under absorption, is induced nuclear fission. So some nuclei do not need a neutron to interact with it to undergo fission, which is why I put induced in parentheses, whereas other ones do need it. So this is just a quick sidebar, or a quick note, is that this is an intro for now. We are going to go more in depth later, both through a guest lecture and another lecture similar to this. Fission is kind of that unique interaction behind special nuclear material that makes it good for self-sustaining fission chains, which are good for both weapons and energy production. So definitely one that we'll give special attention to later. We're also going to give the other interactions special attention later, but in the context of using those interactions to detect neutrons. So again, same process. A neutron is absorbed by a nucleus. Which means that the nucleus is in an excited state. And the nucleus is going to de-excite by splitting into fragments. and neutrons. I will note that the number of neutrons and the fragments, what they are there are many possibilities for them. So we'll draw a picture for this. We'll have a neutron come in and hit uranium-235. And the after picture, we're going to have two fragments. And also neutrons. And so the chemical equation that we would use here is neutron plus uranium goes to an excited state of uranium-236 before it splits. And so this is probably one of the most violent interactions that we know of in nature right now. And so this is one picture of fission. On Monday, Professor Pozzi showed a much better illustration from using a GIF or a video. So this is the best I can do by hand drawing. But these are the interactions. So I'm going to motivate one more idea, and then we'll take a small break before finishing. And I guess what I want to note is, in our example, we've seen two interactions of neutrons with uranium-235. And these have been, they both start the same, neutron plus uranium-235. But then in one case, we got fission, the case right above. And in the other case, we got a uranium-236 plus a gamma ray. And these are pretty different interactions. So we had radiative capture and fission. And it's entirely possible that the neutron could have scattered as well. So I guess the question here is, which interaction will happen? If I put a neutron and a uranium-235 together, which one should I expect? And how do we know which one? And this is a trick question because we don't. It's completely random. And so really the best that we can do is attach some probabilities. So for example, I could say that the probability of fission maybe is 60%, while the probability of radiative capture is 40%. So these probabilities are called cross sections. And cross sections are kind of the next topic we're going to talk about. I see that I kind of went through this a little bit faster than I thought, so I'll pause for a second to see if there are any questions. Otherwise, I'll start with cross sections, and then we'll do questions again after that. All right. So cross sections. And the symbol that we use for cross sections is sigma, lowercase sigma. So a cross section is a quantity in particle physics that quantifies the likelihood of an interaction. Oh, sorry, I see questions. Can I discuss about spallation? I will briefly mention spallation at the end. Oak Ridge has a really cool facility, and they encourage us to use it. And as part of an MTV collaboration, it's super encouraged to go use their spallation source. So we'll touch on that at the end, but we won't really go into depth about spallation today. Are the emitted gamma rays monochromatic or a function of energy deposited in the nucleus? So the question is, do the gamma rays always have the same energy when they come out? And it depends on the interaction, is the answer. Cool. All right, thanks for the question. Sorry, I missed them. I jumped in too quick. But we'll continue to go. So yeah, cross-section is a quantity in particle physics that quantifies the likelihood of an interaction. And these are fundamental quantities that we have to measure. At least not yet can we sit down and determine these quantities from theory. The way that we can think about cross sections, almost as their name implies, is we can conceptualize these as areas. So what that might look like is if I have a neutron coming at a particle, if the neutron interacts in the shaded region, the interaction happens. And if the neutron misses, then the interaction does not occur. And the area of this region is sigma. So the greater the cross section, the greater the chance of interaction. And different interactions have different cross sections. So the way that we can think about this is we can take our picture above and redraw it. And so we'll have a neutron coming in, and our shaded region gets divided up. And maybe there's a cross section for a fission reaction, or a cross section for elastic scatter, a cross section for inelastic scatter, something for radiative capture, and something for which one am I forgetting? You know what? I'm gonna lop transmutation and capture into the same one. Or here, I can give it its own. And what we say then is that the total cross section in this area would be equal to the fission cross section plus the transmutation cross section plus the radiative capture cross section plus the inelastic scattering cross section plus the elastic scattering cross section. So one way we can further conceptualize this probability is, given that the neutron interacts, what is the probability that the interaction is fission? And the answer here is the proportion of the area that is fission relative to the total, or that the probability of fission is equal to the fission cross-section over the total cross-section. So these cross-sections have units, and like our conceptualization, the units of cross-sections are area. So a common unit is the barn, and a barn is equal to 10 to the minus 24 centimeters squared, so very small, or 10, sorry, my handwriting got bad there, 10 to the minus 28 meters squared. And these are areas. So far, we've talked about one type of cross-section, and there are kind of two. What we've talked about so far are microscopic cross-sections. And what we're about to talk about is what we use capital sigma to denote. These are macroscopic cross-sections. And in this equation, n is equal to atom density, or the number of nuclei per centimeter cubed. So microscopic helps us answer questions like, given that the neutron interacts, what's the probability? given interaction, what's the probability of a particular interaction? And what this is a property of the atom. So this is a quantity unique to the atom. What macroscopic cross-sections just do are fold into the equation, like how much of the material is there. So macroscopic folds in density or probability of an interaction in the first place. So do a couple examples along the way. The first is just a throwback to stoichiometry or unit conversion, and it's convert uranium dioxide's weight density which is 10.97 grams per centimeter cubed, to number density. In units of number per centimeter cubed. So what we'll do here, what we want is lowercase n, because on the next example, we're going to use it to calculate macroscopic cross-section. This has units of number per centimeter cubed. So we're going to take the 10.97 grams per centimeter cubed. We're going to multiply it by a conversion factor, which is in a single mole, you will have 270.03 grams of uranium dioxide. So the way I got that is the molar mass of uranium dioxide is equal to the mass of uranium, which is about 238, plus 2 times the mass of oxygen, which is about 16. And then for every mole, we have Avogadro's number of particles, or number of molecules. And so what we get is that the number density is 2.45 times 10 to the 22 per centimeter cubed. So as promised, we're just going to use this number right away. So the next example is if uranium dioxide's total microscopic cross-section is 2,286 barns. What is the total macroscopic cross-section? So we want to use our equation, which is macroscopic cross-section is equal to density times microscopic cross-section. And right now what we have from the previous example is that n is in units of number per centimeter cubed. And currently we have cross-section in barns. It'd be nice to convert the barns to centimeter squared for later so that we have something that's like number per centimeter. So I'm going to do that. So convert barns to centimeters squared. So 2.286 times 10 to the 3 barns is equal to, we want to multiply by a conversion factor, which is 10 to the minus 24 centimeters squared per barn, or 2.286 times 10 to the minus 21 centimeters squared. And so our total macroscopic cross-section is going to be, so n times sigma. The number density we're going to get from the previous example, 2.45 times 10 to the 22 per centimeter cubed. The barns, or the microscopic cross-section, we just converted from barns to centimeters squared. So we're going to multiply by 2.286 times 10 to the minus 21 centimeters squared. And what we'll get is approximately 56 per centimeter. So what I'll note is if we use the total microscopic cross-section, then we get the total macroscopic cross-section. If instead we wanted to look at a particular interaction, such as fission, so if you look at the microscopic fission cross-section, then if we do the same calculation, we're going to get the fission macroscopic cross-section. So keeping subscripts in order. Above, I was using T because that's what the example said. So I originally said that cross-section is related to probability. So cross-sections are related to probability, but how do we get to probability besides understanding relativeness? So larger cross-section means larger probability. How do we get into something where 56 per centimeter means something to us? And one way we can conceptualize it is with a quantity called mean free path. So mean free path, which I'll abbreviate as MFP. Sometimes we give it the symbol lambda, is equal to 1 over the macroscopic cross-section. And this will have units of centimeters. So this is the mean free path to interaction. If I wanted the mean free path to interaction type X, then I would say that the mean free path X is equal to 1 over the total, or sorry, the macroscopic cross-section for interaction X. So yeah, this is the mean path to interaction, or the average distance between interactions. And this is analogous to mean lifetime. And so if you're familiar with the differential equation, I'll go ahead and express it. But if you are not, don't worry. This does not mean that the rest of the lecture is not for you. So the total number of particles is going to be related to 1 over the mean free path times the number of particles. And I'm just going to go ahead and actually skip to the solution here. And what this says is the fraction of particles that survive into a material of thickness X decreases exponentially. And we can rewrite this as the exponent of depth times the total macroscopic cross-section. So what we really need is just this equation. So n of x is number of particles, and I'll say neutrons since that's what we're focusing on today. N of 0 is the number of initial particles. X is depth, and then we define mean free path above. So the example is what thickness of boron, I'll say that this is natural boron, would interact with a beam of thermal neutrons by a factor of 10 to the 6. So what we're saying is I want the fraction of particles that interact to be 1 over 10 to the 6. And what I want to do is calculate X. So what this question is saying is, what is X? So I have to give you some information to calculate this. And disclaimer, I will speed through this part. The notes will be uploaded, but I want to make sure that there is enough time to get through some questions. So the information that you need is that boron, I'll also say that this example encapsulates the other ones. So the breakdown of boron is boron 10 and boron 11. 20% of natural boron is boron 10, and the other 80% is boron 11. And the microscopic, or the total microscopic cross-section for boron 10 is, I'll actually write this as a superscript, is 3,837 barns, and the total microscopic cross-section for boron 11 is 0.005 barns. Last two things you need is that the molar mass is 10.81 grams per mole, and the density is 2.45 grams per centimeter cubed. And now you have what you need to calculate it. The approach here is to first get number density. So we turn this grams per centimeter cubed into a number density, and I'm just going to write the answer here for now. It's going to be 0.136 times 10 to the 24 per centimeter cubed. The next step is calculate the total macroscopic cross-section. So big sigma is going to be equal to 20% of the total density. I'll do this in symbolic form. And this 20% corresponds to boron 10 plus 80% of the density times the cross-section for boron 11. And then the next step, we don't necessarily need to calculate the mean free path, but I'm going to. So we're going to calculate the mean free path. And in this case, it is 0.01 centimeters. So every 0.01 centimeters, we expect there to be an interaction. So now the last step is solve n over n naught equals 1 over 10 to the 6 equals the exponent of minus x over 0.01 centimeters. And if we do solve this, then what we'll get is that x should be 0.14 centimeters. So this is the kind of a back of the envelope way to calculate shielding. The very last thing, there's only one more thing I want to say before I wrap this up. And it's in this example, I very specifically said thermal neutrons, which specifies an energy. And the reason that I do that is that cross sections are dependent on energy, the incident particle's energy. The projectile, the particle that's going in. In our case today, it was neutrons. So if I were to plot this, I'm going to put this in a log-log plot. So if I look at energy and I look at the cross section, then it's not a straight line. So it's not the same as a function of energy. There is some distribution here. And these values for any energy can, so we have to look them up. And I typically look them up with the Janus web app, which is a website, and you can load cross sections and get the information that you need. All right, and that's kind of all I wanted to say on neutron interactions and cross sections for today. So yeah, I'll open it up to questions. I see that there already are some. So Professor Goldston says, in my humble opinion, SI units make this easier. Barns are 10 to the minus 28 meters squared, and number density are generally in the range of 10 to the minus or 10 to the 28 meters cubed. Yeah, depending on what your data is in, some units make it easier than others. For all of my examples, I converted Barns to centimeters squared because density was in centimeters squared. But some people like Barns because then I can say 10 Barns as opposed to 10 times 10 to the minus 24 centimeters squared, just saving me a few syllables and breaths. Yeah. Question here, I'm new to the subject. Why is the cross-section smaller for the larger and more abundant isotope of boron? Shouldn't the probability of reaction be higher if it's bigger and more abundant? That's a great question. And that's because cross-sections were visualizing these quantities as areas, but it doesn't quite have to do with the size of the particle. And that's why we use microscopic and macroscopic. So the macroscopic cross-section, or sorry, microscopic cross-section is a property of the atom. So based on the structure of the atom, how many neutrons and protons are there, the probability of interaction changes. And so there's something special about the atom of boron 10 that makes it much, much more likely to interact than boron 11. The way that we account for boron 11 being more abundant, so there's 4 times as much boron 11 as there is boron 10. The way that we account for abundancy is in the macroscopic cross-section. So the macroscopic cross-section accounts for abundancy. And I apologize for rushing through this. So density tells us the number of particles per centimeter cubed. So inside my jar, how many particles are there? The abundancy tells us that 80% of them are boron 11 and 20% are boron 10. So what we're doing is we're taking the density and saying, all right, 20% of it is boron 10, 80% is boron 11, and then we use this to calculate the macroscopic cross-section for boron 10 plus the macroscopic cross-section for boron 11. But that's a great question. So it does not have to do with the size of the particle. We're just thinking of these quantities as sizes. So to Isaac's question, yeah, great question. I'll read the question first. Are cross-sections representative of literally where an incident particle will interact or collide with the nucleus, or is it a visualization? And the answer is it's a visualization. Once you get down to these particles, we can't picture them. So this is getting into the quantum mechanics. We don't picture them as in one spot. They have distributions in the Broglie or de Broglie, depending on your pronunciation. We get into the part where particles are waves and waves are particles. So this is just a visualization of a pretty complex quantum mechanics value. So question is, why do fast reactors need a higher uranium-235 enrichment in the fission cross-section for uranium-235 is significantly smaller at fast energies, especially given the fission cross-section for uranium-238 is great at fast energies than at thermal? So that, yeah, so if I'm understanding the question correctly, it's why do you need more uranium? Oh, sorry. Is your question, why do I need more uranium-238 than uranium-235 than uranium-238? Or why do I need more uranium-235 in a fast reactor than a traditional thermal reactor? So yeah, why do we need more in a fast reactor versus a thermal reactor? This curve is, so it by no means is completely correct. But this gets into the microscopic versus macroscopic. So uranium-235 is good for chain reactions. And in a fast reactor, so when we look at higher energies as opposed to lower energies, the cross-section is smaller. So what's happening is the microscopic cross-section is smaller. So to make sure that we still have a good probability of fission and fission chains, what we need to do is increase the density to account for the smaller microscopic cross-section. And that's why, and in this case, your density is going to be I'll say fraction of uranium-235 times the density. Well, sorry, I'm going to mix up subscripts. So I guess in words, because the microscopic cross-section is smaller, to make the macroscopic cross-section scale up, you increase the enrichment or increase the amount of uranium-235 so that the macroscopic cross-section does not decrease too much. I think we have time for one or two more questions. Yeah, so we are a little bit over. In general, we're going to shoot for an hour. Different lectures will be longer or shorter, usually on the shorter side. So what I'll do is say that today's lecture is done. A draft of these notes was already uploaded to the Google Drive. I'll upload these specific ones as well. But if you have questions, I'll stick around for a few more minutes and go ahead and answer them. Otherwise, thanks for being here today, and we'll see everyone tomorrow at 3.